Hello everyone, welcome to today's session. I'm Meenu Priya and today we will be learning about groundwater, one of the most important sources of fresh water on the earth. Groundwater is something that we cannot see directly, but it plays a huge role in our daily life. As you can see, the drinking water, agriculture, even maintaining rivers and lakes. So let's explore what groundwater is and how it behaves completely beneath the earth's surface. So generally, what is the groundwater hydrology? You can see here, it is a science of occurrence, distribution, and movement of the water below the earth's surface. This means that we can study where the groundwater is found and how much it is available and how it is going to move through completely soils and rocks. To understand this better, we need to know that groundwater is stored in different type of the geological formations. So in that one, the first one is aquifer. These are the generally geological formation made of the permeable materials like such as the sand and gravel. So they can store the water and also allow the water to move through them. So these are the best sources for the wells and bore wells. Next one is the aquiclude. It is also impermeable. That means water can be stored but cannot move through them. So for example, you can take it as a clay soil. It is a good example of the aquiclude. The next one is the aquitard. These are the materials with the poor permeability. Water cannot flow easily, but slow seepage may be possible, like for example sandy clay. Then last one is aquifers. These are completely impermeable. They don't store, they won't transmit the water, they won't even permit the water. So example, you can take it as a solid rocks. Now we don't know that where the groundwater is going to store. Let's understand the properties that define the groundwater behavior. So the first property is porosity. So porosity is just measuring of the how much empty space will be there between the pores that is existing in the real with the rocks and soil, both the condition. We can calculate by using the formula, and it's defining the porosity that is equal to volume of pore space VI, that you can define that one, volume of pore space by total volume of soil or rock. In the image you can see here great porosity, it is on the left side, lesser porosity on the right side. So highest porosity means more space will be there to store the completely water. The next property is specific yield. So it will tell us how much water can actually come out of the soil or rock due to the gravity. So for this one, the formula is Sy is equal to Vy by V into 100. So Vy defines here volume of the water drained and V is the total volume of the material. For the different type of the soils here, we give the different kind of the yields. So first one is the gravel. It will get the rapid yield. Water drains very quickly here. The second one is a fine sand. It's a moderate yield. The last one is a loam. Moderate yield only, but it will slower than sand when compared to fine sand. So that will explain why wells in gravels are giving the more water. The next property is a specific retention. So this is the amount of water generally that remains in the soil or rock even after the gravity it has drained the completely rest condition. So for this one formula is VR by V into 100. Here VR defines that one volume of the retained water and V is defined the bulk volume of the soil or rock condition. That you can represent the total volume of the soil or rock also. Some water will be stick to the particles due to some kind of adhesion property. It cannot be extracted. So specific yield plus specific retention, both the things that we can combine, you will get the total porosity. So coefficient of the transmissibility that you are defining the T, also transmissivity also you can call. It will tell us how easily water can move through the entire thickness of an aquifer. So for this one formula is T is equal to B into K, where B refers the thickness of the aquifer and K refers the permeability. So when it will get the higher transmissibility means more water can flow into the wells. That is a possibility. Next we are going to learn about the two major types of aquifers, unconfined aquifers and confined aquifers. Let's start with the diagram on the screen here. So as you can see here, the land surface at the top, and below it different layers of the soil and rock is presenting here. So aquifers are the layers that can store and also transmit the groundwater. In this one, figure A, it will show the representing the unconfined aquifer, where the upper surface of the groundwater table is presenting here. This means the water table directly will rise here and falls with the rainfall condition pumping only. Second one, B and C, both shows the confined aquifers, which are covered by impermeable layer, that will call that as a confining layer, because here water is completely trapped under the pressure. When a well is completely driven into that one, the water may be rise above the ground level. We'll see each type in detail completely here. Let's start with the unconfined aquifer. It is also called as a free or phreatic aquifer, which is the simplest one. We also call it as a non-artesian aquifer. So here in this one, the water table, it will form the upper surface of the saturated zones. So whenever the water table will be rise or fall, the amount of the water will be stored in the aquifer. It will also changes. So these aquifers occur very close to the ground surface because they directly receive the recharge completely from the rainfall, from the streams or rivers. They are highly responsive to the seasonal changes. So that when the water table rises here, aquifer will be stores more water. When it drops, the storage will be decreases. So the next one is the confined aquifer. So here will it also called as the artesian aquifer. In this case, so groundwater is completely trapped between the impermeable layers, which is under the pressure greater than the atmospheric pressure normally. So when a well is drilled into the confined aquifer, so water is going to rise in the well, which is level is called as the piezometric level or artesian level. You can see in this one, the kind of see here artesian well, here also artesian well, piezometric level will be fallen there here. So if the pressure is strong enough to push the water above the ground, so the well becomes a flowing artesian well. This one is the flowing artesian well. Above the level it is crossed. So we can see at the B. If the water rises but stays below the ground level, then the well is called as the artesian well here. So like a well C. So since recharge occurs far away at elevated regions, confined aquifers generally have the very low natural recharge capacity when compared to unconfined recharge. So let's compare the two aquifers. In an unconfined aquifer, the water table generally forms upper the boundary. It occurs very close to the surface. It has the high storativity values which is greater than 0.01, and it provides the high yield also. When you take in for the confined aquifer, the water is under pressure due to overlaying completely strata. It occurs at the great depth. It has also very completely low storativity when compared to unconfined aquifer. It will be less than 0.01 and produces a lower than flow yield. Generally, hydraulic conductivity in unconfined aquifer is generally medium. In confined aquifers, it will be ranging from low to medium condition. So by understanding these differences, it will help us to predict how much water can any aquifer can supply. So next we can see the subsurface water division. It is divided into the generally two zones here, zone of aeration and zone of saturation. So I'll start with the zone of aeration. This generally lies above the water table, and the pores which are having the contain the both air and water. It has three subdivisions: soil water zone, intermediate zone, capillarity fringe. So the top layer where the plants get the water, that we'll call it as soil water zone. Intermediate zone is generally a transition between the soil water onto the next zone. Capillarity fringe just above the water table where the water is going to rise upward due to capillarity action. This is a completely zone of aeration, three subdivisions. So next one is zone of saturation. This is the zone below the water table where all the pores are completely filled with the water. This is where groundwater actually exists. So aquifers, aquiters are the parts of the completely saturated zone here. So seasonally, you can see here water table variation, how much it is there. We'll see how the water table changes between the wet and dry seasons. So during the wet season, you can see here there is the more recharge. Water table is going to rise here. So saturated zones and all are expanded here. So when you're taking for the dry season, here you can see water table will be dropped. So saturated zone generally becomes very smaller when compared to winter season, wet season. So this affects the wells, lakes, marshes, streams. So for example, in the dry season, some wells may stop yielding the water, while lakes can shrink in sizes also. You can see here. So the water table is upper boundary of the zone of saturation, you can see here. So below this level, all the pores and fractures are filled with the completely groundwater. So the part above the water table, that we'll call it as the Meadows zone or unsaturated zone. In the figure, you can also see a perched water table which forms when an impermeable layer it is going to exist above the main aquifer, it trapping the water locally. So the springs may form at the such locations, so that we'll call it as a perched water table. So we'll see some of the definitions of the which is related to the groundwater terminology. So storage coefficient, that we'll call it as a storativity. So it will tell us how much water an aquifer can releases per unit decline in hydraulic head. So it is a dimensionless value. So typically values are for the confined aquifer. It is ranging from this value is 0.0012 to 0.00001. If you are taking for the unconfined aquifers, the ranges will be 0.1 to 0.3. So because specifically is main component here in the storage coefficient. So high storativity means the aquifer can store and also it will release the more water. So I'll see the next terminology, coefficient of the permeability. We'll also call it as the hydraulic conductivity. So it will tell us generally how easily water can flow through a porous medium. So units generally it will be centimeter per second or meter per second or meter per day. So what are the factors it is going to affect means it depends mainly on the pore size and how well the pores are connected. So next one is the coefficient of transmittivity. So transmissibility generally it will tell us how much water can move horizontally through the full thickness of an aquifer. So T is equal to K into B. Previously we already saw that formula where K is equal to permeability. So B is equal to saturation thickness, or we can call it as aquifer thickness also. So high transmissibility means aquifer can supply more water to wells. So I think you find the video too easily to understand what is the groundwater, the terminology, and what are the geological formation, what are their properties. So in the next section we'll see about some other topic.